Hello again. I wanted to make another video about entropy and kind of the applications of entropy. In the previous video, I talked about what entropy is and kind of some simple applications in terms of can you decide if it's increasing or decreasing. But I want to go a little further with it in terms of spontaneity and the second law of thermodynamics. So the second law of thermodynamics is basically just saying that the entropy in the universe is always increasing. In other words, the amount of energy in the universe is the same. Okay, that's not changing. Remember, we can't create it and we can't destroy it. That's what the first law told us. But it is always expanding. So the second law of thermodynamics is basically just saying that energy is spreading out in the universe. So this is always true. The energy is conserved, but the entropy is always increasing. Okay? And the book even goes a little bit further to say that the entropy in the universe is the entropy of the system plus the entropy of the surroundings, not unlike enthalpy. We talked about this application in terms of enthalpy. So if the entropy of the universe is positive, right, second law of thermodynamics, then the entropy of the universe is increasing, and the processes are always spontaneous if they are increasing, okay? If the entropy of the universe is negative, then the process is spontaneous in the opposite direction, and we're going to find that true with all reactions. If they're spontaneous in one direction, they're not spontaneous in the other. One of the best examples I can come up with is rust. Rust is always spontaneous. It will eventually happen, but you can't make rust not happen, right? You can't make it go in the other direction. Just like combustion, once it's burned, it's burned. You can't go in the other direction. If the entropy of the universe is zero, then the process has no tendency to occur, and the system is at equilibrium. Now, we haven't talked much about equilibrium. We will in January. We'll do quite a bit of work with equilibrium, but basically means the reaction is at balance, and it's not really going in either direction. All right, so the key to this is really temperature. An exothermic process, as we know, already transfers energy to the surroundings, heat to the surroundings. And this is always a potential energy in the bonds that turns into a thermal or kinetic energy of the surroundings with random motions. Okay? When that happens, the entropy of the surroundings is positive. That's a positive change because there is an increase in temperature of the surroundings. Okay, I hope that makes sense. An exothermic process, okay, will cause an increase of entropy in the surroundings because the kinetic energy increases because there is a release of heat. Okay, an endothermic process, on the other hand, as heat flows from the surroundings to the system, the kinetic energy of the atoms in the surroundings actually decrease, which means the entropy of the surroundings are going to decrease. Okay, hope this is making some sense. When the entropy of the system and the surroundings are in opposition, in other words, one's positive and one's negative, then it's really about the entropy of the universe. And then it means it's basically just dependent on temperature. That's the bottom line. And so let's look at a couple of examples and see if this makes sense. If I'm going to vaporize water, okay, so if I'm going to go from a liquid to a gas, this is endothermic. It's going to take energy to go into the system, right? My change in H is going to be positive. It's going into the system. So my entropy, not enthalpy, but my entropy is positive, okay? Because again, I'm going from a liquid to a gas, so things are expanding. My entropy of the system is positive, okay? Since it is endothermic, the surroundings are going to lose energy. So then my entropy of the surroundings is negative, okay? But when is this true? So we just said when they're in opposition, okay? Then it's dependent on temperature. Well, when will vaporization of water happen spontaneously? Well, anytime we have a temperature over 100 degrees Celsius, okay? And it'll go backwards spontaneous if it's below 100 degrees Celsius, okay? So temperature is kind of the tipping point on whether or not something is going to happen. if those two signs are opposing each other. So really, spontaneity has to do with two things. It has to do with enthalpy and it has to do with entropy, okay? And the impact of the transfer of this energy, right, this heat flow, really has to do, has a big impact of the surroundings, and it really depends on temperature. So if you think about something that is endothermic, it needs energy, right? So it's going to probably run spontaneous at higher temperatures. But the opposite is also true. If we have an exothermic reaction, it's going to actually run better at lower temperatures. Okay. All right, so a little summary here. Number one, if the sign of the entropy of the surroundings, or I should say the sign of the surroundings is really dependent on our enthalpy, our H. So if it's exothermic, then our surroundings increase in entropy, and if it's endothermic, then our surroundings decrease, right? Because they're losing energy. And the magnitude of this entropy really depends on temperature, okay? So the tendency of a system to lower its energy becomes more important at lower temperatures, okay? We'll talk a little bit more about that and give you a couple other examples. So there is a way to solve for the entropy of the surroundings. First of all, it's all dependent on enthalpy, right? Whether it's endothermic or exothermic. So the equation for the entropy of the surroundings includes enthalpy on top and temperature, of course, in Kelvin on the bottom. And the negative sign just helps us to determine the sign of the surroundings, okay? So again, my example is if my reaction is exothermic, so that means my H up here is negative, okay, then the heat flows into the surroundings, and then this will be positive. So that negative sign is definitely necessary. So on your example problem on 16, let's take a look at that. In the metallurgy of antimony, the pure metal is recovered via different reactions, depending on the composition of the ore. For example, iron is used to reduce antimony in sulfide ores. All right, so they gave us this equation right here. Just in case you're not familiar, antimony is Sb. Okay, so they give us this reaction, and we notice that the enthalpy is negative, so that means I have an exothermic reaction. And then it says carbon is used as the reducing agent for oxide ores. Okay, so then up here we see the iron, but down here they're using carbon, just showing a different process. And this one's endothermic, right, because it's got a positive enthalpy. So it says calculate the change in S of the surroundings for each of these reactions at 25 degrees and 1 atmosphere. So again, our equation is change in S over T, right? And don't forget the negative sign. So for the first equation, all we're doing is we're taking our enthalpy right here, and it's negative, okay? But remember the equation has a negative sign. So see if I can do this real quick. Oops, wrong one. Change in H, right, with the negative sign, and I'm going to divide that by my Kelvin, right? And you should get 419, sorry, almost, right here. One thing to note right here, the joules right here, okay, notice there's kilojoules up here. Don't forget to convert right there, okay? So the change in H divided by 298 Kelvin should get you a positive 419 joules per Kelvin. In other words, this is how much energy it increases for every degree of Kelvin. All right, little plug and chug. The second half of it, so this is the endothermic reaction with carbon. Notice again, I have the 778 kilojoules. Same equation, has the negative sign so that my surroundings are going to lose entropy. Okay, and again, don't forget to use that conversion, the kilojoules here, and turn it into joules here. Okay, and then there's this one last concept with entropy, and it really has to do with free energy. We talked a little bit about it last year, so we're going to go obviously a little bit further with it. Free energy is based on Gibbs free energy. If you remember, Gibbs was a physicist, and He was the one that figured out this balance between entropy and enthalpy and whether or not something is spontaneous. And his equation is as follows. Change in G is free energy. It's Gibbs free energy. Our enthalpy, you've seen that before. T is our Kelvin, and change in S is our entropy. Now, H, you already know that is enthalpy. Again, T is Kelvin, and S is entropy. All of these, everything in this equation is the system. So try not to get confused. We're not talking about the surroundings at all. Everything in this is what's happening to the system. Okay? If change in G is negative, then the reaction is spontaneous. If it is positive, it's not. So think of it this way. We already know that negative means energy is being released. So if the entire reaction, once we take into account enthalpy, entropy, and temperature, if there is enough energy to still be released, then there was enough energy for this reaction to run in the first place. If this is positive, if change in G is positive, that means that is the amount of energy that still needs to be put into the reaction for it to run. Okay, so one more time. Change in G, if change in G is negative, then the reaction will run. There's enough energy to run the reaction and then some to be released. That's why it's negative. If it is positive, then that means the reaction will not run unless you input that amount of energy. Okay? And again, the problems that we see with this, obviously some of them are concepts, but if it's a calculation, it's fairly straightforward. The only complication you might see is change in H tends to be in kilojoules, as we saw in the previous problem, and change in S tends to be in joules. So sometimes we have a little bit of conversion to do. An example of Gibbs here, I've got water, solid, ice, moving to a liquid, okay? And we should all know that melting a solid is an endothermic process, therefore a positive joules per mole. And then the change in S of the system, the entropy of the system is also a positive, okay? Because I'm going from a solid to a liquid. There's more movement, there's more chaos in the liquid than there is the solid, so I do have a positive entropy. Is this reaction spontaneous at 10 degrees? Okay, well, we know the melting point of water is 0 degrees, so this is spontaneous, okay? Is it spontaneous at negative 10? Well, no, it wouldn't be. If we're going from a solid to a liquid, again, we know that the freezing point is 0 degrees, so if it's under 0 degrees, we're not going to get this to turn into a liquid. Now that said, water, we know the freezing point of water. So what if it weren't, though? We could take this and we could take this number here and we plug it into the equation here. And that will tell us if it's going to run or not. Okay? All right. So example problem 17, and this is probably the most applicable process for entropy or free energy. At what temperature is the following process spontaneous at 1 atmosphere? Okay, so unlike water, I don't know about you, but I do not know the vaporization point of bromine. For it to go to a liquid to a gas, okay, we can at least make some assumptions. One is it is endothermic. I have to put energy into a liquid to make it into a gas. And because it's going from a liquid to a gas, we're also expanding. It's getting more chaotic. So I would expect my entropy to also be positive. Okay. But notice it didn't say anything about temperature, right? So if we want it to be spontaneous, it's asking for spontaneous. I'm going to go back and use this equation right here, okay? Except I'm going to set the G equal to 0 because that's what I know to be the tipping point between this running and not running. If it's negative, it will run. If it's positive, it won't run. So if I want to know what temperature is going to make it run, I'm going to set G equal to 0 and solve for temperature. Okay. I would suggest that you pause the video, just plug this in, make sure that it's making sense to you. Don't forget that you have kilojoules right here, and you can't put kilojoules on one side and joules on the other. Just make sure you're doing a conversion there before you get your Kelvin, okay? All right, moving on, just a couple of slides left here. When we're talking about changes in chemical reactions, I know we've talked a little bit about it, but we're going to do a little bit of a summary here. The entropy changes in the surroundings are determined by heat flow that occurs in the reaction. And we just talked about that if it's endothermic, then the surroundings are going to lose some of their entropy. And if it's exothermic, then the entropy is going to go up, okay? And we also talked about positional probability, but you really can think of it in terms of chaos. Just be careful not to quite define it that way. A good example would be, if you notice on this side of the equation, I have 4 gas molecules, and then over here I have 2, okay? I went from 4 gas molecules to 2. So just by running this reaction, it condensed. Okay, I have more molecules on the left than I have on the right. So this just means the entropy is going to be negative just by the process of the reaction itself. Okay, so example problem 18 is just predicting entropy based on the reactions. So if I have a solid and it's decomposing, as most decomposition reactions are, I get a solid and then I get a gas. So obviously this is going to expand and my entropy is positive. If I have 3 gas molecules, okay, going down to 2 gas molecules, my reaction is condensing and I see a change in entropy that is negative. Which brings us to the third and last part of this, the third law of thermodynamics. Values for entropy are assigned by comparing individual substances to 0 entropy. Now, when we talked about 0 enthalpy, okay, when we were talking about 0 energy, we said we had to make an assumption of kind of like our sea level, an element in its standard state. Entropy has something a little bit more definitive. It says 0 entropy is a perfect crystal, a solid perfect crystal at 0 Kelvin. Okay, that means there's no molecular motion, so there's no kinetic energy, and it is in its perfect crystal structure state. Okay, and basically entropy from there is always positive. So that's what we're basing our changes on, okay? 0 entropy. I know you've seen this reaction, this formula before in our enthalpy. The enthalpy of the reaction is the enthalpy of the products minus the enthalpy of the reactants. Well, it works for entropy too. And just as a preview, it also works for Gibbs. The Gibbs for the reaction is the products minus the reactants. So these things tend to be, again, kind of a plug and chug kind of thing. Things to be aware of, make sure that you're paying attention to, make sure that you're using your coefficients, make sure that you're putting your products before your reactants, and other than that, they are really pretty straightforward. As you know, I use the examples in the book. I would suggest that you take a look at them, just make sure that you know what you're doing. Just practice them a couple times. I'm sure you'll be fine. Okay. Standard entropy values are in the back of the book. They're in the same appendix that you find your enthalpy values. And yeah, I think you'll be fine. Okay. Know that on the quiz and the test, I will give you those values. Okay. All right. Last part. Gibbs free energy and how we apply those to a reaction. There was only one more example problem, and again, it's just using the products minus reactants. I am going to try and work this problem in class, but again, products minus reactants, you can do it for the enthalpy values, then apply the entropy values, and then of course the Gibbs, all out of the same appendix, products minus reactants. Okay. I went through those last couple problems really quickly because I really think you guys are smart enough not to worry about it too much. Please let me know if you're having any difficulties with these, and I can take it a little slower. Okay. I hope this finds you doing well in this unit, and please let me know if that's not the case. Take care.